Welcome to the Red Hat Enterprise Linux Technical Overview. I'm Steve Bonneville, Technical Curriculum Architect at Red Hat. Before we get started with this video series, I'd like to first answer the question, why do IT professionals need to have experience with Linux? Well, it's possible that the most important technology for IT professionals to understand today is Linux. If you're on the internet, you're already using Linux, even if you don't realize it. Linux is used for more than just running traditional server applications and websites. It's used for point-of-sale systems when you buy things at the store. It's used for stock markets. It's used with smart TVs and DVRs, for the in-flight entertainment system that you might use on your next airplane flight. It's used by the most widely used smartphone operating system in the world. Linux is used for business-critical operations on IBM mainframes and powers almost all of the top 500 supercomputers in the world. It's providing the foundation for new cloud technologies and services and for container-based microservices that are currently emerging in the data center. 90% of the Fortune 500, in some way or another, use Linux or other Red Hat technologies. What is it that makes Linux so great? Well, first, it's open source. You can see how the system works. You can experiment with changes and share code. And it's easier for improvements to be made with the system. You have easy access to a powerful and scriptable command line interface. It's built around a basic design philosophy that allows all administration to be accomplished from the command line interface, simplifying both local and remote administration. Linux is also modular all the way down, and individual components can easily be replaced with improved or altered components. This allows backward compatibility to be preserved or extreme customizations to be made for two different Linux systems. It's possible to make a Linux system extremely lightweight and only run what's absolutely needed. Right now in the data center, if you're running a server application, really only two operating systems matter. And one of them is Linux. And Linux is continuing to be a growing segment in the data center space. If you're a Windows person, you really need to understand Linux so you know how to interoperate with the Linux systems in your environment. If you're doing application development, it's very likely that your application or your application's runtime is going to be hosted on Linux. If you're working in the cloud, your cloud instances may be running Linux, or the infrastructure provided by your private cloud infrastructure or your public cloud infrastructure may be hosted based on top of Linux systems. If you're looking for new job opportunities in IT, as application developers, kernel developers, database administrators, mobile application developers, system administrators, all of those are in high demand, especially if you have Linux skills. The chances are great that if you're working with a new mobile application or an Internet of Things project, the operating system of your device will probably be based in some way on Linux. Now, this video series is being presented to you by Red Hat, but Linux isn't just about one company, it's about the community. It's about a cooperating community of developers, multiple organizations, and corporations that are all cooperating and collaborating to help build the tools that we'll all need in the data center for future innovation. The idea is Linux isn't just locked into one vision or one vendor or one solution. There are many people contributing to Linux. Red Hat's a major contributor, but there are many other organizations, some of which compete with us, some of which cooperate with us, some of which do a little bit of both, that all are contributing to make Linux stronger and better and a much more solid foundation for building the solutions of tomorrow. Linux has always been a major source of innovation in IT. The Web 2.0 was built on top of Linux. The cloud revolution was founded on Linux. It's been driven by the technologies and applications running on Linux. It's been the main operating system used to support cloud hosting solutions. And Linux cloud instances are powering new, innovative, open source and closed source cloud-based applications, big data solutions, software-based storage appliances, software-defined networking are all being built using Linux-based technologies and systems. The emerging technologies around microservices and containerized applications, all the research in that area, a lot of that's being driven, coming straight out of the open source community and being powered by the capabilities of Linux, developed using Linux tools, hosted on Linux systems, and using images built from Linux software. And I think the innovations of the future will continue to be built using Linux. For the rest of this video series, we will provide an overview of some basic Linux administration tools, some basic knowledge about how Linux works, from the perspective of a general-purpose Linux distribution, Red Hat Enterprise Linux version 7. But much of what we will talk about in this series also will apply to other distributions as well. We will look at how Linux is organized, how it works, and we'll provide a basic overview of some introductory system administration tasks. After completing this series, you should be well prepared for further self-paced or formal training about Linux. And I hope that this course will provide a valuable introduction to you as you begin to work toward your mastery of the Linux operating system. What is open source software, and why does it matter? Open source software is software with source code that anyone can inspect, modify, and enhance. Source code are the human-readable instructions that make up a program. Often, that source code needs to be compiled into binary code, into an executable that the computer is actually going to run. Now, all programs are copyrighted from the moment they're created. And so your rights to run a program basically depend on the license under which the copyright holder provides you that software. Traditionally, the way that this would work would be the software developer would give you that compiled binary and license it to you under terms that allowed you to run that binary, but not to provide it to other people. Nor would you have the rights to look at the source code that controlled how it runs. Nor could you change that source code or distribute any changes to anyone else. With open source distribution, it works differently. Again, it's still based on copyright law. The basic idea is it's copyrighted originally by the developer who wrote the software. He may sign over that copyright to someone else or keep it for himself, but either way, the copyright holder then licenses that code to others under an open source license. That license is more flexible than a traditional software license. The license specifies, if it's an open source license, that not only can the customer run the program, but they also can view the source, see how it works. They can change the source to make improvements to it or fix issues, compile it themselves and run the results themselves, and furthermore, redistribute the resulting changes royalty-free to others so that their changes can be shared in general to the rest of the community under the same terms that they originally got access to that source. Now, there's more than one way to be open source, and many different open source licenses exist. The reason for this is the license terms control how that source code can be combined with other code. There's two major classes of open source license. There are copyleft or share-alike licenses that are designed to encourage the development of open source software and to keep code, once it's open source, as open source code. And then there are permissive licenses. They're designed to maximize how much that code can be reused and combined with other code, but which allow that code to be combined with non-open source code or redistributed in a non-open source way. So, for example, a copyleft license would specify that anyone who redistributes the source, with or without changes, have to pass along the freedom for others to make the same changes to the code. This basically is meant to encourage more open source software to become available, that any improvements that are made to the software aren't proprietary but are shared with everybody, and it uses copyright as the underpinnings in order to make sure that these licenses can be enforced and controlled. This is how this works. Some common copyleft licenses include the GNU General Public License, or the GPL, or the Lesser GNU Public License, the LGPL, which provides some special ways that it can be combined with other code for use with shared libraries. Either way, both of these licenses are very widely used in the open source community. The other major kind of license, the permissive license, allow proprietary derivative works or open source works. The idea is you can use the source code for any purpose you like, as long as the copyright and license statements are preserved, and that you follow any other terms of the license that don't restrict its distribution. For example, the license may specify that the person providing it to you is disclaiming legal liability, or there may be some other terms that are in there as well. But the basic idea is these permissive licenses can be reused in combination with more restrictive licenses. So open source code could be combined with code that's currently proprietary, and that proprietary code could be kept proprietary. Or it could be combined with a more restrictive open source license, like a copyleft license, and the resulting code would be distributed under a copyleft license. This maximizes people's ability to reuse this code and learn from it, at the risk of encouraging more proprietary-only improvements. There are several commonly used permissive licenses, the MIT X11 license, the simplified 2-clause BSD license, and version 2.0 of the Apache software license all fall into this category. Whether you're working with a copyleft license or whether you're working with a permissive license, open source promotes improved development practices. It encourages collaborative development between people in different organizations who are working together with open software. It encourages transparency. It's open source. Everyone who's participating in the project can see what's going on. Even people not participating in the project can download the code, look at the code itself, see how it works, learn from it, improve it, evaluate it. It promotes rapid development, in part because there are fewer hurdles to jump over. You don't have to worry so much about, are people allowed to see this? Because everyone's allowed to see this. Another thing that open source development encourages are open standards. Open standards basically, again, in contrast with proprietary standards, are standard ways to do things, standard network protocols, standard ways for services to communicate with each other, and so forth. The idea is an open standard encourages different vendors to implement solutions in a way that's going to be interoperable, that will work well together. For example, if you're providing a standard API that's used for a web service to communicate with another web service, that might, if it's specified under an open standard, it's going to be a lot easier to figure out how to implement that. You could have multiple people try to do better implementations than each other, where if the standard is closed and proprietary and secret, it's going to be a lot harder for improvements to happen. It's going to be a lot less likely for better solutions to be developed, and so on. Open standards provide higher quality due to open collaboration. It prevents vendor lock-in. You're not dependent on just one vendor in order to accomplish something. It improves interoperability between products. It helps facilitate development of integrated solutions in your data center, and encourages standardization. Now you might ask me, if open source is freely available, if anyone can download this source, if people who download the source can share it with anyone, can this be commercial? It's absolutely true that open source products can be used in a commercial way and can support commercial businesses. Open source is a critical part of many organizations' commercial operations today. The internet, the web, cloud services are all built on Linux and built on open source solutions. Open source software may even be offered commercially. The tricky part there, of course, is that the open source licenses grant the right for customers and recipients to redistribute the code, potentially for no fee. So this requires some clever thinking in order to run a commercial business based on open source software. For example, one way that you might do this is to provide help deploying, supporting, or extending the open source solutions. Just because the source is open doesn't mean that everyone has the skill to make changes to it, to evaluate it, to improve it. And that's one of the things that Red Hat provides with our open source solutions, is knowledge, is assistance, is connection with the open source community to help you better integrate open source solutions in your environment. That concludes this topic. See you at the next video. In this video, I'd like to explain what a Linux distribution is and why there are different Linux distributions. A Linux distribution is simply an installable operating system built from the Linux kernel and the supporting user programs and libraries that are needed to assemble a complete system. You see, Linux isn't developed by a single organization, but by a large community of open source projects. A collection of different communities might even be a better way of putting it, each working with individual software components. So what a distribution, sometimes called a distro for short, what a distribution does is it provides an easy way for end users to install and manage a working Linux system. When Linux was originally developed, distributions didn't exist. So the early developers, they'd download a kernel from kernel.org, they'd use various complicated tools to compile it, install it on a system, compile the individual pieces they needed, downloaded from the FTP sites or websites of the different software developer communities, and they'd have to assemble those all by hand. That was actually rather difficult to do. So very quickly the developers figured out that it would be useful to provide what they called a distribution of tools that new developers and new users could use to quickly set up Linux systems. It very rapidly turned out there wasn't going to be just one Linux distribution because there were many different use cases and people wanted different sets of tools for different purposes. And so to this day, many different Linux distributions exist, each with different goals and criteria for selecting and supporting the software that's included in the operating system. A distribution will generally consist of at least a Linux kernel and some supporting user space programs. Now this could be very minimal. For example, for a simple phone application or something, you might not have a normal, complete user space there. Or it could consist of thousands of open source packages and applications, generally not all installed at once, but available for installation. So the distribution vendor has to act as a curator, selecting which programs and which versions of those programs they want to include and support. They have to provide some way to easily install and update that software. And ideally, they need to provide some way to support that software. They should be involved in the community that's developing those programs upstream if they want to be really effective at that. So the role of a distribution vendor is to look at the million-plus open source projects that are out there, be involved with them, or at least be involved with the ones that they're distributing, integrate them into their products, and then make sure that they are sufficiently stabilized for their customer base. And this is the basic model that Red Hat uses when putting together the distributions that we're involved with. I'm going to take a look at two distributions actually today that Red Hat's involved with, and so we can compare and contrast two different approaches. One, Fedora, and the other, Red Hat Enterprise Linux. So the first of these distributions I'll look at is Fedora. And Fedora is a community-driven Linux distribution. While Red Hat's a primary sponsor of this distribution, its direction is very much driven by the participating community, the people who are interested in helping to develop this fast-moving distribution. Red Hat's interest in Fedora is that it provides a way for us to do that second step, that initial integration, to select things that look interesting from the million packages that are out there and start getting them integrated and tested and played with and experimented with by the community to see which ones people are interested in, which ones are successful. But Red Hat doesn't direct the Fedora project. There's two main bodies that currently manage the project. The Fedora Council, which is a mix of both Red Hat representatives and community selected representatives that plan the high-level project goals and manage the finances. And then there's the Fedora Engineering Steering Committee, FESCO, and their job is to actually make technical decisions for the direction for the distribution, select which packages they should include, determine architectural changes the distribution wants to make, handling oversight of the maintainers that are volunteering to assist with the project. And that latter community is entirely selected by the community. The result is that Fedora is a stable and secure Linux distribution focused on new, free, open source technology. Their focus, though, is different than what a commercial organization might want for the long term, because they're focused on innovation, they're focused on excellence, they're focused on trying new things, but they're not focused on long-term stability. They do a major update of the distribution every 6 months, and after a year, their oldest version stops being supported. 2 major updates and they're done. So this has an advantage for the community. It provides a solid distribution for developing new technologies before they're used in the enterprise. And it's an advantage for Red Hat because it's a place for us to integrate and improve that new technology before it goes into a commercially long-term supported project. But for an organization that's trying to support a server for a long period of time, Fedora might not be the ideal choice. When we get to the stabilization phase, Red Hat looks at what's been going on in Fedora, and from that baseline, we develop Red Hat Enterprise Linux, our commercially supported Linux distribution. This isn't just a collection of mature and well-tested open source projects. This is an integrated, complete, enterprise-ready project. And long-term support is an important feature of Red Hat Enterprise Linux. Red Hat supports versions of this distribution for 10 years from the initial release of a new major version. We stay on particular software versions in general, but backport fixes or new features over the lifetime of Red Hat Enterprise Linux in order to continue to support the solution and keep it stable over the long term. We do base Red Hat Enterprise Linux and Fedora, but we pick and choose which packages we're going to support for the long time. We don't include everything Fedora includes. And sometimes we make further enhancements beyond what Fedora has done. When we do, we pass those enhancements back to upstream and to Fedora so that they can adopt them as well in the true open source spirit. This allows us also to make configuration decisions in Red Hat Enterprise Linux that serve the needs of our customers, which might be different from the needs of those of people using the Fedora project. So there's a number of ways this all fits in with the community. Customers can engage with Red Hat to determine the needs of the next release of Red Hat Enterprise Linux. Vendors can engage with us to make sure their hardware and software is well supported in Red Hat Enterprise Linux. And then we can help the changes that are needed happen in the open source community, happen upstream, get back to the community so that not only can we support those for the long term, but those changes can be shared by everybody who's working with various Linux distributions. Red Hat Enterprise Linux is interesting commercially because it's based on subscription support. It's open source. You're not paying for the software license. You're paying for expertise and commitment, assistance with the software, engagement and support when you need it. When new versions become available, you can go ahead and move to the new version when you're ready without paying more. That's part of the subscription. If you're on Red Hat Enterprise Linux 7, and at some point Red Hat Enterprise Linux 8 comes out and you're ready to change that server to Red Hat Enterprise Linux 8, you're not going to be coming back to us and saying, I need to pay for a Red Hat Enterprise Linux 8 license. Your Red Hat Enterprise Linux 7 license can move straight to 8 without any further changes. And these are just some of the advantages that Red Hat Enterprise Linux provides through this subscription-based model. So we can see that there's different ways that distributions engage with their communities. There's different ways that they provide support. There's different advantages and disadvantages that they have. But this distribution model has proven to be so powerful, and especially this two-phase model where we have open integration before providing a commercially supported product, that it's used beyond the core Linux operating system. And we use this model to help test and solidify and support many products by working with the upstream community and then integrating that into products that can be supported commercially for the long term. That concludes this topic. See you at the next video. What is the shell, and how is it used to control programs? The shell is the program that acts as an interface between the user and the operating system. You can think of it as the outermost layer of the operating system, between the user and the system. In Linux, when we refer to the shell, we usually mean a command line shell. This is a text-based program that provides a way for users to interactively run programs. This doesn't require any graphical user interface at all. You can log into a system that's just providing a text-based shell. The shell also provides a simple but powerful scripting language so that we can easily automate commands that we might want to run on the system. The shell program in Linux is modular and is replaceable on a user-by-user basis. Many shells have been used in Linux and Unix-like systems over the years: the Bourne shell, C shell and TC shell, the Korn shell, and others. But the default shell in Linux is the GNU Born Again shell, Bash, and most users use it. This is the same shell that is used by users of the terminal program in Mac OS X as well. To start the shell, first you either log in through a text-only terminal, and it's the first program that starts up, or in a graphical user interface, you start a terminal emulator program, such as GNOME Terminal. The shell is designed so that it can be used to do most tasks. And in fact, the system itself is designed so that shell commands can be used for most system administration. This enables easy local and remote and automated system administration. As I said earlier, you don't need the overhead of the graphical user interface. You can even turn that off completely. This is useful for headless servers and cloud instances. And it's proved useful enough on Linux systems that Microsoft even has put significant effort into both PowerShell and Windows Nano Server to provide similar functionality in Microsoft Windows. The shell is most commonly used to interactively run commands, and these are entered at the shell prompt. A typical command may consist of up to 3 parts: the name of the command itself, followed by some options that affect the behavior of the command. These typically are marked by 1 or 2 leading dashes to show that they're options, as opposed to the / character in Windows. And then those are followed by arguments that may be the targets of the command. So for example, a command to rename a file might start with the command to do that, followed by the name of the file you want to rename, and then the name that you want to use. So let me show you some examples here of a basic set of commands. First, here's the command date that I'm typing in at the shell prompt. The result of this command, when I hit return, is to print out on the terminal the current date and time. It takes no arguments or no options in this example. Here's another example. I could use the ls command. This will list the files in the current directory. It lists all the names out to the terminal. If I type ls followed by the -l option, that changes the behavior of the command to list more information about modification times and permissions on those files. An example of a command that has an argument as well would be the wc command. Wc can be used to count the lines or words or characters in a text file. I'll say wc-l, I'm interested in the number of lines in a file, and I'll specify the name of a file name here, and hit return, and it tells me that there are 6 lines in that file. One more example here. I could use the head command lines equals 3 is my option, followed by the name of a file. This will display the first 3 lines of that file. Now in this case, this file only happens to have 1 line, so it displays the entire file, and then I get the prompt back. So these are all examples of simple commands, but they show how commands and options and arguments all work together at the shell prompt. Now the shell has a number of features to make it easier to run commands and to type long command lines. One of these features is tab completion. If I start typing the first few letters of a command and hit tab, the system will attempt to complete the name of that command. But if there's more than one command that might match, I'll need to hit it a couple times, and it will show me the list of possible options I have. So let's say I want to run the hex dump command. I could type X and tab, and it will go ahead, the system will go ahead and fill in the rest of the command for me. Or I could have put an A there, and it would have completed head instead. Likewise, we have file name completion. I can start typing the name of a file and press tab, and if only that one file name matches, if there's only one file name that matches, it'll go ahead and display, it'll actually type in the rest of the name of the file. If there's multiple possible file names that match, again, if I hit tab twice, it should list all of the possible names that would complete that particular file name. If any file name that would start with those characters, I should say. So this can save on a lot of typing in the shell. Another powerful option in the shell is I/O redirection. This allows us to send the output of a program to a file. For example, earlier, I listed detailed information about all the files in this directory. Let's say I wanted to save that to a text file. Now I could try to figure out how to cut and paste something from a terminal or type it in another terminal program, but the easy way to do this would be to redirect the output of the ls command into a file. And I can do that by typing the angle bracket pointing toward the name of the file, and then the name of a new file to create. And now, instead of displaying the output on the terminal, it's actually saved it into that saved information file. So if I said, again, head lines equals 3 on that file, there's the first 3 lines of the output of ls-l. So this is another really useful capability of the shell. Another useful function it has is the shell command line history. I can type the command history, and it will list all the commands that I have run recently. Here, the last 78 commands. I can rerun a command by typing an exclamation point and the number of that command. So if I type exclamation point 75, the ls-l command will be rerun. It prints that to the terminal, and then we see the output of the actual command. Another option is I can use the arrow keys to scroll back and forth through the history. And the powerful thing about this is then I can use that to edit a command and run it again with slight changes. If I'm concerned about keeping a history of my commands on the system, it's always possible to clear my history by typing history-c, which will remove the current history and start over from scratch. Now I mentioned that the shell is useful both for local and remote administration. There's a command called SSH, Secure Shell, that can be used to connect to a remote system. It takes as an argument the username of a user we want to connect as, and then an @ sign, the name of a machine I want to connect to. I'll probably be prompted to authenticate as that user in some way, possibly by typing that user's password in. And then if I do that successfully, I'll get a new shell prompt on that remote system. And now at this point, I can run commands on that system as if it were local. So this provides a lot of power to remotely manage systems that might be in another room or even another city from me. Now, when you're done with a shell prompt, you can exit it by typing the command exit. In the case of a secure shell session, that will close that session and you'll get your original shell prompt back. If you logged in through a text terminal, that will close your session and drop you back to the text login screen. Or if you've opened a terminal window, it will exit your shell and close the window. This introduction to the shell only covered some of the most basic features of this extremely powerful tool. We didn't talk about job control and how to manage more than one process at the same time from the shell prompt. We didn't talk about pipelines, which is a very sophisticated way to build up complicated commands or get interesting data from multiple different smaller commands. We also didn't talk about shell scripting or some of the shell scripting control constructs like for loops that can be used both in scripts and in powerful ways from the command line. I encourage you to learn more about the shell and to learn more about these advanced features on your own. It's a very powerful tool and one which you should be very comfortable with as a Linux user and administrator. That concludes this topic. See you at the next video. In this video, we're going to talk about how programs work on the system, and we're going to take a look at three things: what the kernel is and what it does, user space, the rest of the programs that run on the system, and then we'll take a look at some simple commands to get information about running processes and stop them. The kernel is the heart of the Linux operating system. It's responsible for scheduling running programs. It's responsible for managing hardware for user programs. It's responsible for managing the memory on the system. If you have a device driver, it's running in the kernel. If you are working with networking, it's running in the kernel. The kernel is responsible for managing the security of the system and making sure that users can't interfere with other users' files or that external attackers can't break in and cause damage to the system. The kernel's job is to support user programs, and all the rest of the programs on the system run in what we call user space, as opposed to kernel space, kernel code such as device drivers and so forth. So, for example, if you run a program on the system from the shell prompt, it's a user program, and it runs in user space. These interact with the kernel through special devices or system calls that they make. An individual running program is called a process, and each process has its own private virtual memory space. It runs as a particular user and set of groups so that it can access particular files on the system. It has a state, whether it's currently running, whether it's waiting to run, whether it's blocked waiting for a disk to complete, and so forth, and a unique process ID number, a PID or PID, that's used to identify it. Now there are several different types of process on a Linux system. We have user processes. These are generally associated with a particular user. They were generally started by being run from a shell prompt, and therefore they're associated with a terminal. They print their output to a terminal, they get input from a terminal. Generally, if they're getting input from a terminal, we call it a foreground process because they control a shell prompt. It's possible for a process to be put into the background, in which case they're currently not taking input from a terminal, but they can display output to that terminal. Then we have a second class of processes called daemon processes. These are processes that aren't associated with any terminal at all. Typically, they're started up by the system and provide things like network services or do other special housekeeping tasks to keep the system running. And then finally, we have a third class of scheduled process, kernel threads. These are parts of the kernel that are running as if they are regular user processes or system daemons. They're not associated with a terminal. They're parts of the kernel, but they're still scheduled as if they were regular processes. We can get information about the processes on the system by using the ps command. As an example, if I just run ps by itself at a shell prompt, you'll see that it will print out the commands that are associated with this particular terminal for this particular user. But I can add additional options to get more information about processes on the system. For example, if I add the AUX options, A means list all the processes on the system, X means even those that aren't associated with a terminal, and U will list the user that those processes belong to. And you'll see we also get a bunch of additional information about those processes. Looking at this output, we can see that there are a number of user processes, daemon processes, and kernel threads here. User processes will be associated with a particular terminal. Daemon processes aren't associated with any terminal at all, and in this column we see a question mark. We can tell that a process is a kernel process if we look over here and we see that the name of the command that was being run is in square brackets. That concludes this topic. See you at the next video. In this video, I'll be talking about the Linux graphical interface. This interface is divided basically into three major components. The first component is the X window system. The X window system provides the basic infrastructure that's used by graphical applications in order to draw things on monitors and to take input from the keyboard and the mouse and make sure they get to the right graphical applications. The second component is the desktop environment. This is the set of core graphical applications that's used by the user in order to provide their basic graphical desktop environment. That is, how do they get to files? How do they see what time it is? How do they start new programs from the graphical interface? And then thirdly, we have individual graphical applications, such as Firefox or OpenOffice, or other tools that users might use that could work with different desktop environments. In Red Hat Enterprise Linux version 7, our desktop environment is a set of programs, I should say, called GNOME 3. GNOME version 3 is one desktop environment that's available, but others are also possible and are available in Red Hat Enterprise Linux. In order to work with GNOME, we first have to log on to the system. Here is an example of the login screen that a user might see when they first want to access the graphical interface. Let me click on my username here and log on to the system. So you can see here, this is the basic desktop environment that users can work with. We have some icons over here. For example, this one that I can click on provides a graphical way for me to explore the file system and look at files that I might have. If I double click on one of these, it'll automatically open an application so that I can work with and edit this particular file. We have menus up here on the top bar that allow us to start various applications. If I use this to start a terminal window, for example, you'll see that there's a little icon down here at the bottom that I can use to minimize or maximize that particular window. GNOME also has a feature called the Activities Overview. If I press the Windows key on this system, that will pop up shortcuts to start a number of different applications. So I could start, for example, a web browser in this way, or close it again. In the middle, I can see all the windows that I currently have open. So if I start another terminal window, and it's hiding another application window, by pressing the Windows key, I can see all the different windows that I have, select the one I want to work with. And I can see which one's which based on a little miniature icon here of what's on the screen. Over here on the right-hand side, I have access to different workspaces. So I can switch to a different workspace that's clear and start new applications here and leave my windows on the other workspace intact so I can switch between them to give myself more room to work. If you've worked with systems such as Mac OS X, they have a similar system that provides more space for users to run their applications. I can drag these windows from one workspace into another very easily using this activities overview. Because you're likely to be using a terminal quite frequently, there's another shortcut to quickly open a terminal. You right-click on any space here that doesn't currently have a window in the main background, and there will be a menu item, Open in Terminal, that will immediately open a shell prompt for you, saving you a little bit of time. Finally, up here at the right-hand side of the screen, we have another menu that provides settings so that we can adjust the networking of this system if necessary, especially if this is a laptop that's being used as a workstation of some sort. We have a way to log off, so I can select log out and log out as this user, ending my session. Or I can temporarily lock the screen, or if this is the physical system, power off or reboot the system. That concludes this topic. See you at the next video. In this video, I'm going to talk a little bit about files in Linux. One reason I'd like to talk about it is because files are particularly important to Linux systems. That's because file input and output are used for many different purposes in Linux, to the point at which people often say, we try to treat everything like a file. That's not quite true. It's probably better to say that from a programming perspective, we try to let programs handle a lot of I/O as if they're writing to a file descriptor, a handle for a file, as a stream of bytes. That's a little bit more technically complicated, but the idea behind this is simple. What we're trying to do is to simplify the programming environment. So as often as possible, we can use the same system calls and the same functions to work with different kinds of things, whether those are regular files, whether those are hardware devices on the system, whether those are network connections that people may be communicating over. All of them can be handled as a stream of bytes, and all of them can be read and written as if they are some sort of a file on the system from a programming perspective. As far as files on the actual file system are concerned, Linux only keeps track at the operating system level of 7 different types of files. These 7 types of files are regular files, the typical data files that you're generally going to be working with, or programs that you might be running that are stored on the system, directories or folders that are going to be containing other files, symbolic links, which are simply special files that point by name to another file somewhere else on the file system, device drivers, I should say devices, divided into 2 broad categories, character devices and block devices, representing something you write to as a stream of data, like a tape, or something that you tend to put a file system on, like a hard drive. And then named pipes and sockets, which are specialized files that are used for processes that want to talk to each other. In general, most of the time, you're going to be working with regular files and directories, but occasionally you may find yourself working with some of these other types of files. So one reason why this is important, as I've said, is that file I/O and device I/O can be as similar as possible. And so programs that can do file I/O can actually write and read directly from devices. Let me show you a quick example of this. For example, on this screen here, I'm going to run the hexdump command on a file. So I'll type hexdump -n512, which means read the first 512 bytes, and print out ASCII characters as well as the actual bytes for this file. And I'll use the README file, which is a short text file. So we can see here the actual characters in the text file. This is an example file, a short sentence. And then over here on this side, I can see the actual hexadecimal data that's in that file. So we're looking at the raw file as if I were as a programmer looking at an executable. So This is interesting, but let's say that I want to take a look at the hard disk, and I want to look at the actual hexadecimal data that's stored on blocks on the hard disk. In an operating system like Windows, if I was using the Win32 API, I'd need to use special system calls and write a specialized program that would have access to the device and know how to talk to the device drivers and work with the Windows kernel in order to do this. On a Linux system, I'll be able to use the hex dump command directly on a file representing the hard disk. On this particular system, the hard disk is provided by a device called devvda, which represents the whole hard drive. So if I run hex dump -n512-c on the devvda file on this system, and you know I'd better be the super user in order to do this for security reasons. So let me change my user very quickly here. Let me try that now. That's dumped out the first 512 bytes of that particular disk directly to the screen. So I can actually use this to view the contents of the disk and troubleshoot it for errors. And you'll notice I did this with a simple command that could be run from the command line that's normally used to work with regular files. This is a really powerful capability. If you think for a moment, think about the implications here. If I can do this, I could use a tool that would dump the contents of the file out to save a disk image. If I can write to that device that I just looked at, I can use this to take a file that's that saved disk image and write it back out to the disk, basically reformatting the hard drive and putting data on that hard drive. Now, I'm not going to do that here because obviously that would wipe out my system. And that's one reason why, just like any other file, these files will have file permissions on them, blocking people from doing things if they are not authorized to do so. That concludes this topic. See you at the next video. How are files and file systems organized on a Linux system? On a Linux system, all of our file systems are organized into one unified hierarchy of directories and files. It's an inverted tree of directories. We call it an inverted tree because we think of the root of that tree being at the top, and then the branches are directories, and the files at the end are the leaves on those branches. So all of the files that are accessible to a system are organized in one unified file naming scheme, one unified tree of directories. There aren't separate drive letters that you shift between to look at files on different disks. Simply changing into a new subdirectory may cause you to transparently change which disk you're looking at, which storage you're looking at that may store those particular files. This is the same basic hierarchical organization that a Macintosh OS X system would use, but we have a slightly different organization in terms of how we lay out these directories than they do. So in this diagram here, we see that at the top of the tree, we have the root directory, which we'll just refer to as a slash for short. And then under those, we have a number of different directories or possibly files. And then under those directories, they may have subdirectories with more files, which may themselves have subdirectories, and so on and so on. In order to navigate this directory, we need to know how to refer to files. A file can be found by following its absolute path from the root directory. We list all of the directories between the root and the file, starting with slash for the root and ending with the file name. And each directory separator on Linux is going to be another slash. So for example, on the diagram here, we have this folder that's labeled mark, this directory labeled mark. Its absolute path will be /home/mark to refer to that particular directory. This directory down here would be /home, /mark, /docs, all run together. That's the absolute path to that particular directory. Each of these directories is used to store particular kinds of files or data. And on the table on your screen here, you can see a list of some of these directories and what they're used for. Another way that we can refer to the location of a file is through relative paths. That is, we can specify the location of a file relative to the current working directory. Let me show you this on a shell prompt with some commands. So the pwd command lists what our current working directory is. And you can see here this is /home/student. The ls command lists the names of files in this directory. And so that README file there could be referred to as /home/student/README. The cat command will dump out the contents of the file to the screen here. Or I could simply refer to it by its relative name, cat README, because /home/student is my current working directory. There are two special directories, dot, which is the current directory, and dot dot, which is the parent of this directory. So if we look again at that diagram from earlier, we had /home/mark. Dot, if my current directory is /home/mark, is /home/mark itself. Dot dot, its parent directory, is /home. So if I'm currently in home student and I type ls dot dot, that will list the contents of /home, which just happens to be that one directory on this system, home student. So I mentioned earlier that as you change directories on the system, you might transparently change which particular disk you're on. So for example, simply from changing from the root directory into /home might change which disk I'm on. If I were to do that on the system that I've illustrated here, in that case, I'd be on another disk and see the files on that storage. This is actually a very powerful concept because if we need to expand storage on the system in a particular directory, I can add a new disk, copy the files in that directory onto that disk, and then make that particular directory a mount point for the new file system. That is, when I change into that directory, that's going to contain those files on that new disk. Finally, I'd like to talk about some basic file management commands, which I'll demonstrate here on my shell prompt. I mentioned pwd to list the current working directory. Some other useful commands, cd to change your working directory. So if I type cd ... that will put me in /home. If I type cd home student, typing the absolute path, that puts me back in /home/student. I've mentioned ls to list the files in a directory. Another useful informational command is df, which will list the mounted file systems. So / is this disk device, devvda1. And if I were to change into one of these other directories, these would move me into other special file systems on this machine. Finally, there are three commands that you should know about to manipulate files. mv will move a file from one place to another. So you can use this to rename a file. For example, I can use cp to create a copy of a file, and we will see that these files are identical in size. Use rm to remove a file that I don't want to have anymore on the system. That concludes this topic. See you at the next video. In this video, we're going to talk about a text editor that you can run from a shell prompt called vi. Why are we talking about a text editor in this video? Text editors are important to system administrators because so many of the configuration files on a Linux system are set up as text configuration files. So being able to log into a system remotely, start a text editor up in a text-only shell prompt, and use that in order to edit files is a very important skill. Red Hat Enterprise Linux follows a standard called POSIX that specifies many of the basic utilities that should be provided on the system. VI is one of those basic utilities, so you can expect it to be installed on the system, pretty much any system that you're likely to run into. The implementation of VI that Red Hat Enterprise Linux includes is a program called Vim, VI Improved, which adds some additional optional features that aren't specified by the standard. Let's take a quick look at how VI works. To start VI, you can simply type the command VI followed by the name of the file that you want to edit. If the file doesn't exist, it will be created the first time you save it. Now you can see from my terminal window that VI's interface doesn't provide a lot of hints about how to work with this tool. And for this reason, many people get a little nervous the first time they use VI because they find it a little bit difficult to wrap their heads around. But I'll tell you, there are only a few basic commands you need to know to be effective with VI. The thing to remember is that VI operates in two modes, command mode and edit mode. It starts in command mode, and the idea in command mode is any key that you might type is a command to VI to tell it to do something. And probably what we want to do is put it into edit mode, where we can actually start editing this file. So if I type I, that will put VI into edit mode, particularly into insert mode. And you'll see down here at the bottom, there's the word insert to remind you which mode you're in. At this point, I can use the keyboard normally and start typing in the screen. I can use my arrow keys to navigate around. Type a few more words in here, and so forth. If I want to exit edit mode, I can type the escape key, and that will put me back into command mode. That's a useful tip if you ever get lost when you're working in VI. Hit the escape key a couple times, and that way you know you're in command mode, and you know what commands you can run from there. Now I could go back into insert mode with I could exit it again with escape, but let's say I want to save this file. In order to save my work, I'll type :W, short for write, and it will write my changes out to that file that I specified earlier. If I want to save my work as another file name, I could type :W and type some file name here. And it'll be saved to that file instead. You'll notice if I save another time, again, it'll go back to the original file I was working with. In order to quit VI, I can type :Q, and that will exit the program. So remember, VI file name to start it up, I puts you into edit mode, escape takes you out of edit mode, :W writes, :Q quits. That's enough to get some basic work done. Let's take a look at one more trick, which is how to easily copy and paste in VI. To copy and paste, I need a way to highlight text. So in command mode, I'll type V, which will put this into visual selection mode. I will select some text, and then to yank a copy of it into my clipboard, I will type Y. So Y is kind of like I'm copying the text in. I can put my cursor where I want it, make sure I'm in command mode, type P to paste, and it will paste that text right there. And then, of course, I can save my work. One last tip, if I type :WQ together, it will save and quit in one step. VI has a lot of advanced capabilities and a lot of cool things it can do. One great way to learn more, if your system has the Vim Enhanced software package installed, is to run the command vim tutor, which will start up a short tutorial actually in a VI editor that you can run through to learn a little bit more about Vim. It goes into quite a bit of depth. You can do a little bit of it at a time, but it is a very useful resource that's available on the system. That concludes this topic. See you at the next video. In this video, I'd like to talk about users and groups in Linux. Why do we have users in Linux? Linux is a multi-user system. We may have more than one person wanting to use the system at the same time. We have different processes running on the system that need to have private resources from each other. The kernel uses users and groups to provide security barriers, to isolate one user's files and resources from another's. Those might be two different human beings using the same machine for private files. That might be an Apache web server that shouldn't have direct access to the raw database, but instead needs to work with a database program to get access to the pieces of the database to which it is permitted access. There's three broad classes of users on a Red Hat Enterprise Linux system. We have regular users, the human beings who are using the system. Then we have system users. These are also non-privileged users, just like a regular user, but these system users are used by programs in order to isolate them from each other. So the Apache web server might run as a user, maybe user HTTPD. The mail server might run as its own user. A MySQL database might run as its own user. And that way, these different users can have files that are private to them, or if that program is compromised by a remote attacker, those programs have limited access to other things on the system. Finally, we have the super user. This is a special user called root. This user controls everything on the system. If you're logged onto the system as root, you can make changes to the system. You can access any file on the system. You can kill any process that's running on the system. Likewise, we have groups. A group is simply a set of users on the machine. Each user has one primary group and must have one primary group. That group typically, for a regular user, is a group that has the same name as that user on a Red Hat Enterprise Linux system by policy. It doesn't have to be. And the reason why we do this is so that we don't have to have all the users on the system in some catch-all group by default. They can all be in a private group of their own, and if they need access to other resources, they can be added to the groups for those other resources. Just like users, a group may be granted access to a particular file or a particular directory or other resources on the system. So aside from that one primary group each user has, they may also be the member of multiple other supplementary groups. The main distinction is, while supplementary groups are also used to determine whether or not a user has access to a file, if that user creates a file, the file is generally only owned by one group. And the group that's chosen by default is that user's primary group. Let's take a look at some commands to see how we can figure out what user a shell prompt is running as and what groups that user may have access to. The ID command, when run at a shell prompt, provides a lot of detailed information about the user that's running that particular shell prompt. Here we see this prompt is running as user student. That user's primary group is group student. And they're a member of two groups. Besides group student, they're in group wheel as a supplementary group. Processes on the system also run as the user that started it, the primary group of that user, and then the secondary groups belonging to that user. And we can see this information with PS. We saw earlier, if I type PS AXU, it will print all the processes on the system and list which user those processes are running as. If we want to know what groups those processes are running as, I have to type a special command. I'll add the -O option here, which says I want special output. And I say I want to know the username, the process ID number, the primary group, the list of supplementary groups and the name of the command. And so here I see username, primary group, supplementary groups, and the actual command that that user is running. Another useful thing that can be done from a shell prompt is I can change which user I'm running as. I can start up a new shell as a different user. And in order to do that, one command that's useful is su. If I type su followed by a dash and the username of the user I want to log in as, I'll use the root user in this case. I'll be asked for the password for that user unless I'm already super user. So I have to know what that is. And if I type it incorrectly, I will get a shell prompt running as that user. If I'm done running as that user, I can simply exit the shell, just like I would if I had SSH'd into a remote system or was done with a terminal session, and I'll be dropped back to my original shell prompt. Because you frequently want to log in as the super user, if you don't specify a username, that's the user that's assumed by default. One other hint that's provided as a safety mechanism if you're logged in as the super user is that the shell by default changes the prompt to show a number sign rather than a $sign here, so that you can see that you're logged in as the super user and have administrative authority over the system right now and could theoretically run commands that could cause major damage if you aren't careful. One other command that's useful is sudo, S-U-D-O. Sudo followed by any command will attempt to run it as the super user if you have authority to do so. Let me show you an example. I'll try a cat a file called etsy-shadow, which I know only the super user can read. I'll get a permission denied error since I'm currently running as student. If I type sudo cat etsy-shadow, if student has privileges to run the sudo command as root, I'll get prompted for my own student password, not the root password, and then it will go ahead and run that command and dump that information out to the screen. The advantage of this is that those users who have sudo privileges don't have to know what the permanent root password is, they just need to know their own passwords. And also the commands they run get logged. The cool thing about this is it's very easy to add a user to have authority to run sudo, because all you have to do is make sure that one of their supplementary groups is group wheel. And we saw earlier that student is in group wheel. To do that, we can run a command called usermod. So if I said sudo usermod dash a capital G wheel student, that would, if I hit return, prompt me for my sudo password and would go ahead and add that user to group wheel. Finally, let's talk about commands that can be used to add new users to the system. Obviously, this is a privileged operation, so you'll need to be root in order to do this. So I will go ahead and switch to the root account. And now I'll run some commands here. User add will add a new user to the system. And if I don't care too much about the defaults, I can set up a new regular user simply by typing user add and the name of the user I want to add to the system. Right now that account's locked, it needs a password, and so we'd need to set it. There's a number of ways to do this. I'll pick the simplest one here. I'll type as root password with the argument of the username, and as root, this is how I can change users' passwords to anything I want. It won't ask me for their password. I can just go ahead and type anything I'd like. Now that that's been done, I could go ahead and say su and switch to that user. Since I'm root, it won't prompt me for that user's password. That user account exists and is working. Finally, the command group add, followed by the name of a group, will create a new group that I can add users to. Again, just like I added users to group wheel earlier, I could say usermod ag my group new user, and that user now has that as one of their supplementary groups. That concludes this topic. See you in the next video. In this video, we're going to talk about file permissions. Linux has a simple system that's used in order to manage access to files that is yet powerful enough to accomplish most of what you need pretty easily with its basic functionality. Let's talk a little bit about how it works. Basically, every file is labeled with a set of permissions, and there's only three broad categories of permissions that the basic file permissions system supports. The user that has access to the file, that owns the file. The group that owns the file has a certain level of access. And then all users on the system that aren't that user or a member of that group are granted a certain level of access to the file. And then there are three levels of access permission that files have: read, write, and execute. If you have read access, you can read the contents of the file. If you have write access, you can write to the file. And if you have execute access, you can run the file like a program. So it's probably a binary or a shell script or something similar. So let's take a quick look at how you can tell what permissions are set on a file. And then we'll talk about the differences between how they're interpreted on regular files and directories, because that's kind of interesting. So let's look at my shell prompt here. I'll do a long listing with ls-l of the files in this directory. And that provides a lot more detail about the latest modification time and the file permissions on each of these files. If you look at the first part of a file name, you'll see a bunch of characters here. Those list the file permissions for this particular file. And then the second part here lists the user and the group that owns this particular file. So another file here is owned by user student, group student, and has this set of permissions. So how do we interpret these permissions? The first character on these permissions indicates what kind of a file this is. Is this file a regular file? Or is this file a directory or one of the other 7 file types that Linux recognizes? If it's a dash, it's a regular file. If it's a D, it's a directory. If you see something else, it's one of the other kinds of files. As far as permissions are concerned, this just affects a little bit about how those permissions are interpreted. Then we have 3 groups of 3 characters that follow. The first group of 3 characters represent the permissions for the user that owns the file. The second group of 3, the permissions for the group. And the third group of 3, the permissions for everybody else that's not in either of those 2 categories. If there's an R in the first place, they have read permission. If there's a W in the second place, that category has write permission. And if there's an X in the third place, they have executable permission. If you see a dash instead of those characters, they don't have that right on that file. So in this case, for the file another file, user student can read and write the file but can't run it as a program. Likewise, user group can read and write the file but not run it as a program. And everyone else on the system can only read that file. Directories are treated slightly differently in terms of how they interpret these permissions. On a directory, if you have read access to the directory, that means that you can get a list of the file names in that directory. You can't access the contents of the directory, you can just find out what files are in there. If you have execute on the directory, you actually can access those files in the directory, get information about their permissions and how big they are, and also access their content if their file permissions permit you to do so. So most directories, if you have read-only access on them, will grant you both read and execute. Write permission on a directory means that you can create or delete any file in that directory. So let's compare this, for those of you who are familiar with Microsoft Windows, to some of the differences between how Linux permissions work and Windows permissions work. Unlike NTFS, Linux permissions only apply to the directory they're set on. Permissions aren't automatically inherited by the contents. So if I say I'm going to set permission for to allow you to read and execute a directory, that doesn't automatically grant read and execute to you on every file in that directory. It doesn't change their permissions in any way. On the other hand, what it does do is it means that those permissions of those individual files can take effect. So I can use permissions on a directory to block you from accessing files in that directory. So a file could be in a directory readable by everybody. The file could be readable by everybody, but if the directory is not readable by you, you won't be able to get to it. Another way that we can think about this is equivalencies. So if you have read on a directory that's in Linux, that's similar to list folder contents in Windows. If you have write on a directory in Linux, that's similar to having modify permissions to that directory in Windows. And if you have execute on a directory in Linux, that's similar to traverse folder in Windows. Another way you can think about permissions too is that the root user effectively has full control of all the files on the system. They ignore regular permissions completely. And since we are going to care about what they're set to, we need to know how to change them. And there are 3 commands that we're going to use very quickly here in order to manipulate file and directory permissions. Those are chmod, to change the permission modes that we have on the files, chown, which changes the owner, the user that owns the file, and chgroup, which will change the group that owns the file. Chown and chgroup are pretty straightforward. If I run chgroup, the name of a group I'm a member of, and a file name, I should be able to change that file so that it is owned by that group. Now, if I'm a regular user and I'm not a member of that group, the system won't let me change that permission. So if I were to say instead chgroup mail another file, student's only a member of group student and group wheel, I'm not going to be permitted to change the owner of another file to mail. If I were super user, if I were logged in as root, I could do that. Likewise, the chown command looks something like this: chown username file name, and we'll change that file to be owned by that user. That command only works for root, so in order to make this work, I'll use the sudo command to run that. And if I take a look now at another file, you'll see it's owned by group root because root's permitted to do that. And I can change that back again to student without any difficulty. The last command that we should look at is chmod, which is used to change the permissions on the file itself, whether it's readable, writable, or executable. The basic way this is going to work, let's look at another file. Right now it's readable and writable by user, readable and writable by group, and read-only by all other users on the system. The basic idea is that I can say chmod and specify a mode. U for the user, G for the group, or O for all other users on the system. So let's say I want to give everybody read-write access to this file. I'll say chmod for other, add write to another file. And you'll see now other has write access. I could say chmod group remove write from another file. If I look again, you'll see that group no longer has write access to this file. And you just use the same letters that you have here. So if I want to add read or remove read, I'd use an R. Add execute or remove execute, I'd use an X. So fairly straightforward command in order to change file permissions. There's a couple other ways to do it, and there's ways to set more than one permission at once. I won't go into those details here today, but if you're interested, you can take a look at the documentation. That concludes this video. You may now move on to the next one. Any Linux distribution needs a way to install and update its software. There are many different approaches that can be used in order to manage software. Red Hat Enterprise Linux uses a package-based model. The idea is that software is assembled into individual packages, and those packages can be updated, downloaded, installed as a unit on the system. This has a number of advantages over, say, an image-based solution where you download an entire image of a core piece of the operating system. It tracks which version of which package is installed. It tracks what software packages have been installed and what packages installed which files. This makes it easier to update those packages, to uninstall them and remove all the files they put in place, to make sure that any dependencies those packages have been appropriately met. In other words, if that software requires some particular version of another piece of software, we can ensure that that is also installed on the system. And this package-based model makes it a lot easier to manage those dependencies. Red Hat Enterprise Linux and Fedora and a number of other distributions use a particular implementation of package management called RPM package management. This is based around a special archive format called RPM package files. An RPM package file consists of three main pieces: an archive of the files to be installed, both the executables and any data files or documentation that might be needed, any scripts that should be run when the package is installed or uninstalled, and information about the package, metadata, things like the name, release, and version of the package, what other packages it needs to work, any packages it might conflict with on the system, and so on. The idea is that these package files are just like zip archives in that you can download it as a file to the system. It's easy to move from one system to another. Once it's there, you can use a command to unpack it, and then that archive file can go away because it's been unpacked and the installed files are already on the system. Now, before we look at how we install and update and remove packages, let's take a quick look at how we name packages and how we keep track of which packages are newer than others. RPM packages have a standard naming and versioning format. If we were to look at the file name for a particular RPM package, that file name reflects the name and version and release of the package. So we divide up the name into several components. The first part of the RPM file name is its name. In the example here, HTTPD tools is the name of the package. So if we were trying to install the package by name, that's probably how we would refer to it. Then there's a version string. It comes in two basic parts, version and release. The first part, version, reflects the upstream community version of the software that we're installing. So if I were to go to the Apache HTTPD site and find the software that was used to make HTTPD tools, their 2.4.6 release is what was used to build this RPM package. Then the release part of the version is which update of this RPM package is this. In other words, it might be that the first time the 2.4.6 package was put together, worked fine and was distributed, but then we found that there needed to be some enhancements made, or we wanted to fix some bugs that were found after release, or there were other packaging changes that we wanted to make, maybe to add some optional components that weren't originally shipped. In that case, we'd increase the release version of the package, indicating this is a newer package, but the version would still be the same because it would still reflect the original upstream version of this software. How do we know if one version of a package is newer than another? Well, if first we look at the name. If the name of the package is the same as another package, then it's the same software. The one with the higher version is going to be the newer package. If both packages have the same version, then the one with the higher release will be a newer package and will update the older one. So how do we get RPM updates? Well, let's think of what we have to do. We need some way to download these updates from wherever they're distributed from, and then we'll need to install them. We might also need to update any dependencies that package would have. With Red Hat Enterprise Linux, we have a tool that does both, yum, that both downloads packages and helps us manage, install, and update them. These packages are provided from a repository on the network, and yum needs to be configured to know how to find them, what mechanisms to use to reach that repository of packages that can download them. These can be downloaded from our content distribution network through Red Hat Customer Portal. This requires that the machine has internet access. Optionally, you can set up an add-on service, Red Hat Satellite Server, at your organization, which can be a local set of those packages for a number of different versions of Red Hat Enterprise Linux. That satellite server can be used to manage your subscriptions, manage multiple systems. You can actually do a lot of advanced things in terms of monitoring your systems with that tool. Either way, the way we would configure an individual server to get official updates is similar, and that's what we'll look at in a moment. There's a third way you can get packages, and that's to get them from supplementary sources through what are called standard yum repositories. And these are configured by text files that you place in a particular location in the etc directory, and generally are downloaded using normal HTTP protocol connections to a web server. We won't talk about that in as much depth here. So let's take a quick look at the commands that it takes to set up a Red Hat Enterprise Linux system to get official updates from the content distribution network. The first thing we have to do is to set up that machine with a valid subscription for Red Hat Enterprise Linux. And there's a simple command line tool called Subscription Manager that can be used to do this. Let's take a look at my prompt here. Before I subscribe this system, I'm going to need to log in as root. Let me run Subscription Manager Register to contact the Red Hat servers and download a subscription. It wants my customer portal username and its password. I have to type that password right as well. This will take a moment. And the system has been registered and has a valid subscription associated with it. Actually, I should say it's been registered to get the valid subscription. I need to attach the subscription next. That's the next step, Subscription Manager attach. This will actually apply the subscription. It will guess what the most likely subscription is if I have multiple possible options. This will take just a moment. And once that completes, it'll tell me what it's been subscribed to. In this case, it's the attach process picked the standard Red Hat Enterprise Linux server channel. The next step is to see which yum repositories this automatically configured or made available to me to configure so that I can get software packages. So I can use the yum repo list command to see which repositories were automatically configured by the subscription registration process. Let me do that very quickly here. Now in my case, I'm an employee at Red Hat and my account automatically entitled me to a lot more channels than you'd normally see. A typical server would probably just show up with the rel server RPMs repository as a default choice that would be chosen by this process. If I want to disable some of these extra repositories, I could do that with the yum config manager command. Say -- disable, and then before the slash here would be the name of the repository that I would want to disable. So if I don't need rel SAP for rel 7 server RPMs here, I can say I want to disable that. And then that particular, it prints out a whole lot of extra output. That particular repository has now been disabled and I won't get package updates from that particular repository. Now that I've set up updates, I can use the yum command in order to install, update, or remove packages from the system. For example, I could simply run yum update. When I do this, this will attempt to see if my system's fully up to date or not. And if it's not fully up to date, it will install the latest version of the packages, looking at all of those repositories I currently have configured to see which ones are which one has the newest version of the package available, and also makes sure that any dependencies I need that have changed are also downloaded and applied. So it will take a few seconds for this command to run. It'll print out a long list of packages, and then At the end of that process, I will be asked whether or not I actually want to apply those updates, which in this case, I won't. If I wanted to just install or update a particular package, I could say yum install, and if I know the name of the package, specify that package by name. So if I want the ZSH Z shell package installed, I can say yum install ZSH. It will find that package, and if I say yes, download it. Since this is the first time I've done this, it wants to make sure that I have the right keys installed here to validate that these packages are really from Red Hat. I will set that up very quickly here. Now that package is installed. Now anytime I do a package install after this, I won't be asked about those keys again. It will assume those are the correct keys for the system and will use those to validate any further packages that are downloaded. If I don't want that package anymore, I can simply say yum remove ZSH. And again, it'll show me what will be removed because that package and anything that depends on it will be removed. And it may be that removing that package will also remove something I want to keep, at which point I would abort this command. But I'll go ahead and say yes for my example. Finally, if you're trying to find out what packages are available or which ones are installed, there are some useful yum commands that you might use in that case as well. Yum list will list all of the packages that are installed or available on this system. If I were to type yum list installed, this will only list packages that have been installed on this system. It won't list ones that are available from other repositories that might be configured on this system. If I see a package here I'm interested in and I want to know more about it, I can use the yum info command. So I could say yum info zip, for example, and this will print out information about the package, what its current version and release are, which repository this version of the package is coming from, or if it's installed, and detailed information about that software package. Another useful way to find packages by keyword is to use yum search. I can say yum search followed by some keyword, I'll use kernel here, and it will find any package where that matches, where the word kernel matches either in the name of the package or in its short description. That concludes this topic. See you at the next video. In this video, we're going to briefly look at how network interfaces are configured and at some troubleshooting tools and informational tools that can be used to get information about the system's network configuration and check to see if things are working. Let's talk briefly about how networking and network interfaces are configured in Linux. Every network port on the system is named. It's associated with a network interface name. And each of those network interfaces needs to be configured. So let's take a look at how these interfaces are named first, and then we'll look at the configuration system. There's a standard way of naming interfaces on the system, as you can see in the table on your screen. Any network interface that starts with EN followed by some additional characters and information is a physical Ethernet interface. It actually is on physical hardware and has a port on the system. WL would be a wireless LAN interface, Wi-Fi access. Anything that starts WW would be a WWAN interface, something like a cell phone card that has a network address, and so on, perhaps on a laptop or some other special device. These are all physical interface names, and they're mapped in a predictable way to the actual hardware on the system. So those names can be tied to which card it is, on which PCI bus, and various system interfaces can be used to see which ones are available. Now, traditionally in Linux, before these predictable device names came along, most Ethernet interfaces were simply named ETH something. So ETH0 would be your first network interface, and ETH1 would be your second network interface, and they weren't tied to hardware in any way. Interfaces with names like this are still very common on virtual machines or other systems where we can't determine what the hardware is. So let me show you some examples of a couple network names very quickly. Using the IP command, IP_addr_show will show both the interfaces and what addresses they're currently configured with on a system. Here on my test system, this shell prompt, if I type IP_addr_show, this is on a virtual machine, and I can see that I have two network interfaces, ETH0 and ETH1, that are associated with IP addresses and other information. But since this is not a physical machine, it's not mapped predictably to hardware specifically, it's just represented as a generic Ethernet address. This LO device, which you'll also see, is the loopback interface. This is one that will exist on any machine, even one that doesn't have networking configured, so that it can talk to itself over the network. Now, I happen to have another machine sitting here, which I will switch to very quickly. On this machine, if I type IP_addr_show and this long name, ENP0S20U3, this particular interface is on PCI bus 0. Hexadecimal address for the port is, the decimal address for the port is 20. Its hexadecimal address, I think that would be 16. And U3, it's the third unit on that particular interface. In this case, this is a physical Ethernet to USB adapter that happens to be plugged in on this specific hardware. So once we know the network name, the interface name of the network interface we want to configure, then we need to provide it with the right information. So what do we need to configure on the system to make sure that networking is going to work properly? Well, the interface needs to know what IP address it's been assigned and what the net mask is of the subnet it's attached to. The system needs to know the IP address of the default router and which interface to try to use to communicate with that router. And the system also needs to know what the IP address is of the DNS name server that it's using for name resolution. Now, most commonly what we do is we tell a system to get this information by configuring a network interface to use DHCP, the Dynamic Host Configuration Protocol, in order to talk to a server on the local subnet that will automatically provide it with this information. But that also has to be configured to tell the system to bring up that interface and to do that. In Red Hat Enterprise Linux 7, we have three components that help us more easily manage our network interfaces. The first of these is Network Manager. This is a system daemon, runs all the time, that monitors your network interfaces, checks to see whether or not they are plugged in or not, have link, or if they're a Wi-Fi interface, whether a particular Wi-Fi network has gone away or appeared that it should be associated with, and make sure that the correct configuration is activated when that link is available. Then we have a command, nmcli, that's part of Network Manager, that can be used both to manage those interfaces, to administratively bring them up and down, and to change their configuration. Network Manager stores all of this configuration information in text configuration files that are kept in the etc sysconfig network-scripts directory. And all nmcli does when you reconfigure one of these interfaces is save that information to one of those files and then let Network Manager know that it needs to change the current configuration of that interface. So let's take a quick look at how that works. So the nmcli command, as I mentioned, is a command line tool that we can use to see information about our connections. Now, from the perspective of Network Manager, a network interface is called a device, and a set of connection information, like an IP address, DNS server, and so forth, that should be applied when that connection is live, is called a connection. So if I type nmcli con show, this will show all the connections by name. Here I have system eth1 and system eth0, and whether they're active right now or not, and if so, I should see a device name over here showing which interface they're associated with. In this case, the ETH0 and ETH1 devices. The information for these configurations is actually stored in etc sysconfig network scripts, as I mentioned. And if I look in there, I'll see there's a ifcfg eth0 and ifcfg eth1 file, both of which contain text information. Oop. I have to actually type the correct path to the file. Text information about how that particular interface should be configured. I can also say nmcli dev show and get a whole bunch of information about the current settings of one of these interfaces. So if I'm getting information through DHCP, for example, the information that we got from the DHCP server can be reported with conn show and dev show. I can see what devices exist and what their current settings are this way, and so on. So this is another tool like IP that can be used for these purposes. So if I want to change the connection information used for one of these interfaces, there are two ways to go about it. One of them, which many experienced system administrators find convenient, is simply to directly edit the configuration files. So I could go to etc sysconfig network scripts and open ifcfg eth0 in a text editor, and I could go in here and actually directly change my settings. Once I did that, then in order to make sure Network Manager knows that those settings have been changed, I would have to type nmcli conn reload to tell it to reread those configuration files. This has the advantage that it's fairly easy to replace that file and reload it. The disadvantage for a new system administrator is you may not know what all those directives are or how to set them. The other way that we can change these connection settings is to use the nmcli conn mod command. So nmcli conn show followed by the name of a connection will show me all sorts of information about the connection. So I can see what the name of the connection is. I can see what it wants to set the DNS server to, what it wants to set IP addresses to, and so forth. But I could also say something like nmcli conn mod and specify that I want to set a particular IPv4 address. So I could say IPv4.addresses should be 10.0.0.2 on a network with a /24 subnet mask, and hit return, and that would change those settings and would actually edit the configuration file. So that's another way to do this. Some of the most common parameters that would be adjusted are on the table that's on the screen. IPv4.addresses to set address and subnet mask for an interface. IPv4.gateway to set the default router IP address, if that's available on this link. IPv4.DNS to set the name server's IPv4 address statically. And then IPv4.method. If you're setting all of this by hand to specific settings, you would use manual to say to use the static information only. If you wanted instead to get all of this information from a DHCP server, you set all of these to the null string. Basically just put a pair of empty quotes as the option to set for these. And then for IPv4.method, you set auto, and will automatically try to use DHCP to configure your network interface. One last useful pair of commands when working with network interfaces through Network Manager: nmcli conn up, followed by the name of the connection. So for example, system eth0 in this case, makes sure that that connection has been brought up and is active. If I want to turn off the interface, rather than say nmcli conn down, normally what I want to say is nmcli device or dev disconnect. And the reason why I would say dev disconnect instead is because remember I said Network Manager watches to see if the interface has link. If the interface the interface still has link, and the daemon will realize this. And if I said con down, it will figure, oh, well, the link's still there. I should come back up again. Dev disconnect tells Network Manager, no, I really want to administratively turn off this interface for now. Finally, let's talk about a couple other simple troubleshooting commands to test to see if your configuration is actually working properly. Probably the most fundamental command for testing your network connection is ping, which sends a special packet to a remote system to see if it's reachable. And if that system is reachable, it should respond with a ping response, an ICMP echo response. So if I say ping and give the name of some other system on the network, I should see a response with, and it will also keep pinging that system, showing me if I'm losing any packets, since it's sending about 1 a second, and about how long it takes for my network traffic to reach that host. You can stop the ping by typing Control-C. It's possible that you can reach a system and have ping not work properly if it's behind a firewall of some sort that's filtering ping requests, but not filtering other traffic. Another tool that's useful for testing connectivity is traceroute. You type the traceroute command and then the host name or IP address of the host that you want to see if you can reach. In this case, it will show the IP addresses of the routers between you and that system until it finally reaches the system at the end here. In this case, so each hop between where I'm currently running this machine and the server that's providing www.redhat.com to me at the moment is listed here. You'll notice hop 12 just lists stars. A router doesn't necessarily have to respond to traceroute if it's busy. Presumably, hop 12 was too busy to respond, but it did pass the traffic on to the next one. Again, firewalls sometimes can block traceroute, but not block other traffic to a system. But this can be useful to help you diagnose if there are problems that are outside your network, and therefore potentially not your problem. That concludes this video. You may now move on to the next one. In this video, we're going to take a look at the Red Hat Enterprise Linux 7 boot process. We'll talk about how the system starts up and how you can control which system daemons and other services are started by the system at boot time. The startup process varies depending on the hardware that you're on, at least the first few stages of it. But let's take a look at a standard 64-bit x86 based system. The first thing that happens when you power on a system is the hardware goes through a power on self-test. And then the firmware runs, and after it's validated that all the hardware is working properly, its first job is going to be to try to boot an operating system. The way it normally does this is to run a small program called a bootloader that loads from the disk somewhere. How it loads it depends on what kind of firmware you're using. In Red Hat Enterprise Linux 7, our bootloader program is called grub2 and works with the two main ways that a x86 system might boot. The legacy way, using the BIOS, and the new way, using UEFI. If the system's booting from the BIOS, what the firmware is going to do is it's going to look in a little section of the disk outside of the partition table, outside of any file system, load that bootloader, and execute it. If we're on a newer UEFI system, what's going to happen is the firmware is going to load that from a file system. Either way, the firmware loads this bootloader program, like I said, called grub2, and then grub starts executing. Its job is to make sure that the system's ready so that we can run the kernel. And then once it is, it's going to load the kernel and execute it, and also loads a little file system called the initial RAM disk that provides any device drivers the kernel immediately needs before the system has fully started up. At that point, the bootloader exits and has handed off control to the kernel. The Linux kernel goes through its startup process, starts up its device drivers, and takes over control of the hardware. By the time it's gone through its complete initialization process and is ready to start up other programs, the Linux kernel is fully operational, has taken control of the system, and will keep running until we shut it down. But at that point, all we have running is a kernel. We haven't fully set up the system environment, we haven't mounted all of our file systems, so we don't have access to all of our files, and certainly we don't have any way for a user to log in. So the next thing the kernel has to do is to start the very first user space process on the system, PID1, the initial process. It is the responsibility of the initial process to start up all of the other programs that are going to be running on the system, whether those are system daemons that are running in the background providing services, or whether that's a login screen so a user can log in interactively and do various productivity tasks. Different programs have been used for this initial process over the years. Originally, Linux used a system based on AT&T System 5 that would run a program that would run through a bunch of shell scripts and start up a whole bunch of things, mount all the file systems, start up all the programs, and then that program would be done. Today, in Red Hat Enterprise Linux 7, we've replaced this initial process with a more modern replacement called systemd. And most Linux distributions today have been switching to systemd as their PID1 process. So we're going to have to figure out how systemd works, how it determines what processes should be started up, and how we can control that. Systemd thinks of system daemons as individual services. So the web server would be provided as a service. The printing subsystem would be provided as a service. If we're turning on other network services, databases, and things like that, we might have to activate particular services to ensure they're started automatically at boot time. Both systemd and the older systems that replace it mainly care about two things: whether a service is enabled to start automatically at boot, and is that service currently started or stopped. So what we're going to need to be able to do is either to tell the system to start that service right now, and also to tell the system whether that system should automatically be started on the next time the system boots. To do that, systemd comes with a tool called systemctl that's used to configure and manage its services. We can get information about what systemd is doing with systemctl as well as configuring things. Let's look at some basic commands here. The first one we'll use is systemctl status. This command will print out all of the processes that were started in some way by systemd. So I'm not going to worry about trying to explain all the details of what it's telling you here, but if I scroll down a little ways, we will see the names of a bunch of services that systemd is managing. And under the names of those services, we see the names of processes those particular running services have started up. So presumably at some point, the HTTPD service was started, either manually or automatically at boot, and that led to the following 6 processes with these PID numbers to be started. And those are currently running. So this is a good way to get a picture of the status of the system and what's associated with what services. So in this case, that HTTPD service is providing the web server on this system. So that's currently running and available. Let's say that I don't want the web server running right now. I can say systemctl stop httpd.service, and that would stop that particular service. Now, if I hit return here, we don't see any particular feedback. There's a couple ways I can check to make sure that that's stopped. I can say systemctl status httpd.service specifically, and it will tell me it's currently inactive and has been for the last 13 seconds, and has some other information in the logs here about that service, what its process ID last was, and so forth. If I wanted to restart that, I could say systemctl start httpd.service. That will immediately start it right now, so it should be running again. And we'll see here that now it says, yes, it's active and running. We have a bunch of new HTTPD processes. Notice they've got different PIDs than we had before. and it's currently started and available. So the systemctl start and systemctl stop commands start and stop a service right now. But if I were to reboot the system, whether or not that service is running depends on whether it's enabled to start at boot or not. So if I said systemctl stop httpd.service, but this service is enabled to start at boot, it would automatically restart again. And if I look here in my output from earlier, you'll see that sure enough, this particular service is enabled and will start automatically at boot. So let's say I want this stopped right now, systemctl stop httpd.service, and I want to make sure it will not start even after a reboot of the system. I will say systemctl disable httpd.service. And we'll go ahead and disable that so that it will not start again when the system reboots. If I change my mind, instead of saying disable, I will say enable. And again, now that will automatically be started the next time I boot the system. One other question is, when the system starts up, how does systemd determine exactly which of these enabled services should be started? Does it just start all of them? Can we configure things so that we start some of them? Systemd has a concept called a target. What a target is essentially the group of services that we want to have running. And when systemd boots, the way it figures out what services to start is it picks a target and starts all of the services associated with that target. There are two primary targets that the system has available. Graphical.target, which starts up the standard system, any enabled services, and the graphical user interface. And multi-user.target. Multi-user target is only going to start up the text login, and it'll also start up any other system daemons and things that should be running in the background. But it will disable the graphical login screen. So if you don't need to have the X Windows system in your desktop environment running on some server, it's very easy to make sure that you only start up the multi-user target. We can see which of these targets this system will use by running systemctl get default. And this particular system will boot with the graphical environment turned on. If I type systemctl set default multi-user.target, the next time I reboot the system, it will not turn on the graphical interface automatically. This won't change anything right now. It changes what will happen in the next reboot. If I wanted to change which target I'm running right now, I would have to say systemctl isolate, and then the name of the target. So since this is presumably currently running graphical target, I would have to say systemctl isolate multi-user target. And what that will do is turn off anything that multi-user target doesn't need. So presumably the graphical target pieces will be turned off. The graphical target includes multi-user target. Multi-user target obviously doesn't include graphical target. So if I say I want to start graphical target, that will start up everything for multi-user target and some extra stuff. If I say I just want multi-user target, it will ignore that extra stuff that graphical target starts. To figure out what exactly that is, we have one other command that's useful, systemctl list dependencies. So if I say systemctl list dependencies multi-user.target, this will list all of the services that will be started or that may be started with multi-user target. If I say systemctl list dependencies graphical target, it shows everything that graphical target starts, and you'll notice that on that list is multi-user target, and therefore all of the stuff under here that multi-user target includes will also be started. Rebooting the system and shutting it down is also tied to the initial process, whether it's systemd or something else. There are two basic commands to do this. Reboot, which will reboot the system immediately. and shut down, which will cause it to shut down and power it off. That concludes this topic. See you at the next video. In this final video, I'd like to talk briefly about some ways that you can get help online and a couple resources that may be available to you to learn more after you're done with this series. First, let's look at some online tools. The first piece of online documentation that you should be aware of are the system man pages. The man pages basically are a programmer's manual that's provided online. This contains information on commands, library functions, file formats, system conventions, and so on, organized into standard sections, and each page follows a conventional format. Many years ago, this was printed out and provided as a binder in the machine room. In the modern day, we look at this online through commands on the system. It's structured as a reference, not a tutorial, so sometimes you have to pick and choose what you're looking at in the man page to figure out exactly what you're looking for. So the manual's divided up into numbered sections, and in the table on your screen you can see what some of these sections map to. Typically, most of the things that you're likely to look up would be user commands in section 1, or system administration commands in section 8, perhaps the format of a configuration file in section 5 of the manual. Using the manual is relatively straightforward. I will show you over here in my terminal window. The shell prompt, you simply type man, followed by the name of the man page that you're interested in. If you know what section it's in, you can specify the section number first, and then provide the name of the command that you're interested in. So if I type man1 ls, it will find the man page for the ls command that we used earlier to list the directory contents on the system. And here it will have documentation on all the options for that command and possibly some other information about that command. You can page through it a page at a time by hitting the space bar. You can back up with page up or with arrow keys to go back and forth through the document. And once you're done, you can type Q in order to quit looking at that page. The reason why sometimes it matters which man page you're looking at is that there may be two man pages with the same name in different sections. So if I just type man PASSWD, it'll show me the password command in section 1 of the manual to change my password. But if instead I'm interested in the format of a file called /password, I may need to type man5 PASSWD, so it will look at that page instead. And again, the system generally guesses that you're interested in commands first and will prioritize looking for the name in that section rather than other sections of the manual. Another way you can try to find things in the manual is with a man-k command, which will search by keyword. So if I typed man-k PASSWD, it will search through the list of man pages and try to find every man page and description that includes the string PASSWD in it. For more help, you actually can type man, and it also has its own man page. Another useful reference are the info pages. Info is an online help system originally developed by the GNU project for software packages that were developed by people participating in that project. Info documents tend to be set up more as hyperlinked documents and written more like actual user manuals. The way you start that up is similar to man. You type info and the name of the info document that you're interested in. So for example, if I type info ls, in this case, it will actually jump into a document called core utils. There's a page on the ls command in there that it will look up, and it knows, info will guess that that's what I'm looking for here and open the right page. And I can scroll through this document, again, much like I did with man, and I can obviously run this command in a text-only terminal, so I can access this even if I don't have a graphical interface available on the system. As it's organized like a book, so I can go N to go to the next section of this document, or P to go to the previous one. And if I continue to go previous to section 10.1 here. It'll say there's nothing earlier than this. If I go up, it'll go up to the header for chapter 10. If you see something like one of these asterisks here, that's probably a hyperlink, and I can go there and hit return, and it will jump me directly to that section. When you're done with info, you can type Q to exit that tool as well. Info tends to have more in-depth information than man pages, but again, this is also going to be a fairly technical command reference and provide technical documentation. A third help system that may be available to you if you're using a graphical interface is the GNOME help system. You can type the F1 key in the graphical interface and it will start up a graphical program that provides help for you with various information on the graphical user interface and applications in that interface. It's not necessarily complete for all graphical applications on the system, only those that come as part of the core GNOME desktop environment. One interesting thing about this particular tool is that in some cases there are short videos as well as text tutorials that are available. Besides the online resource, there's also other resources available to you through Red Hat's customer portal. If you go to access.redhat.com in your web browser, you can access everything associated with your subscription in one location. That includes access to information on solutions, frequently asked questions, and other articles provided through our knowledge base. Some of these articles are freely available to anyone without login. Others are only available if you've logged into the portal through a subscription. You also can manage your support tickets through this portal and download software, download updates, get evaluation subscriptions in this way. For more information, go to access.redhat.com/help for help with getting access and setting up your account there and making sure it's properly associated with your subscriptions. Once you do have an account set up and associated with subscriptions, there's actually another tool you can use online to access the customer portal without a web browser. This is Red Hat Support Tool. Let me show you a little demonstration of this as well. So if I run the command redhat-support-tool on this system, if I hadn't connected it to it before, it would probably prompt me for my account name and password to demonstrate that I should have access to Red Hat Support Tool. To see what I can do from here, I can type the question mark, and it'll list a whole long list of commands for help, more than are visible on my screen here right now. But one of the most useful ones if you're looking for help is the search command. Let's say I want to learn how to create a logical volume. I can say search, create logical volume, in quotes here. Oh, now it wants my user ID. Let me put that in. And I'll save the user. It wants my password. That I won't save. And you'll see here on the screen it's come up with a list of possible matches of articles and solutions that are available on Customer Portal. However, the first one looks like a really good match for me here. How can I create logical volumes on Red Hat Enterprise Linux? So I'll select Solution 1, and I'll be prompted in a moment here with a list of different parts of that solution I can look at. The title, what the issue is that's trying to be solved, some information about the environment, like what version of Red Hat Enterprise Linux or other software is available, and so on. Let me just display all the sections. So you can see here, here's the title of the article, or the solution in this case, a direct URL you could use in a web browser, maybe to view this in a more comfortable way, and then some details about the issue, the environment, and in this case, the resolution, how you solve this particular issue, along with a bunch of other information. Once I'm done with looking at this article, I can type Q to quit. I can type Q to bail out all the way to the command section here. Now, let's say I happen to know the article number in knowledge base. The KB command actually lets me look that up directly as well. So if I type that with knowledge base article 18666, that's that logical volume article again. And so that's another way to look up information on Customer Portal. Customer Portal also provides documentation that's freely available with or without a subscription about many system administration tasks, installation tasks, and other things that you'll find useful. I strongly encourage you to spend some time looking through that documentation as you learn how to use Red Hat Enterprise Linux better. One final resource that I want to mention, I'm part of Red Hat's training organization, and Red Hat does provide formal training and certification on how to learn how to use Red Hat Enterprise Linux and our other products. After this video series, if you are ready for further formal training from Red Hat, you may be interested in taking a look at some of our courses. In particular, perhaps our initial system administration course, Red Hat System Administration 1, RH124, which is a good fit for people who are new to Linux and interested in learning more about the topics that we've discussed in brief in this video series. We offer our training in many different delivery modes: instructor-led, virtual training, self-paced online learning. We even have a training subscription that you may find interesting that gives you access to all of our courses and provides access not just to learn about Red Hat Enterprise Linux, but tools such as Ansible, working with our Java middleware solutions, working with software-defined storage, and many other really awesome things. Thanks for your time, and enjoy learning more about Red Hat Enterprise Linux.